Okay, these are the bending stress examples I'm going to do for the class lecture. There's 4 or 5 of them. Just going to go through them based on what we've been doing so far. They're pretty straightforward. This is example 4.1, page 305 in your textbook. A nominal 8 by 12 timber member shown below is used as a beam subjected to vertical loading, right? For maximum bending stress, the beam is oriented so that the long dimension, the 12-inch dimension, is vertical. Calculate the section modulus of the beam with respect to the axis of bending, which is the XX axis, right? And use dress dimensions. So a bunch of words in here maybe you haven't heard. We're going to look at page 496. This is going to be Appendix E, okay? And that's a appendix talking about structural timber. And if you look, this is an 8 by 12, right? So I have it here. This is an 8 by 12. Some of the key things you want here, there's 8 by 8, 8 by 10, 8 by 12. Its dress size is going to be 7.5 inches by 11.5 inches. Things you want to grab here. We don't need the area necessarily. We don't need the weight. We can use I and C together, or we can just use the section modulus. If you recall, the section modulus is the combination of C and I together. Let's just grab that or just check it. The section modulus here is S of X is, and that's obviously the long orientation, is 165 cubic inches. Nominal is, it's called an 8 by 12, but the dress dimensions are actually smaller, 7.5 by 11.5. And it says calculate the section modulus, and that's S is equal to the moment of inertia over C. We can calculate that BH cubed over 12, where B is 7.5 and H is 11.5. And that comes out to BH squared over 6 when you do the math, right? If you do that, you get 165.3 inches cubed. That matches the chart. So that's just a check on that, right? That's where they get that. Second question, these are going to be like 3 or 4 in a row that have the same beam. Example 14.2. So the timber member from the last example is used as a simply supported beam. Now we're going to put it on supports the long way, right? That's the long way. Over 16 feet, carrying a uniformly distributed load of 400 pounds per foot. So 16 feet of 400 pounds per foot, that's going to come out to a point load, an equivalent of 6,400 pounds in the middle. Calculate the maximum induced bending stress, and that's that sigma is MC over I. Neglect the weight of the beam. The beam weight's important in this, and in all kinds of structural calculations, just not in this example, okay? So same beam as before. The actual dimensions of the base are 7.5 and the height 11.5. If you think about it, this is a case right from the handout I gave you or the back of the book, right? So this is going to be, instead of doing a shear moment diagram, what we could have done is we could draw it like I did with all the steps, or you can use Appendix H in your book, right? And in Appendix H, this is simply going to be case 1, right? And here, we want to know the bending stress, so we'll have to know the bending moment, the max, right there. And that's going to be WL squared over 8, where in this case, L is 16, right? And W is the 400 pounds per foot. And that's basically what this calculation is right here, right? It'll come out the same way. Here I just did the area of this triangle, so the point right here, I know that it's going up 3,200, that's a 6,400 UDL. I'm up 3,200 because of the reaction, right? It's 3,200. Basically, this UDL converts to a point load of 6,400 pounds from inspection. Each reaction must be 3,200. So I'll do this the long way. Shoot up 3,200, go down linearly 6,400 to minus 3,200, and shoot back up and close it up. The point here is the sum of, is this area, which is the base, which is 8, right? The height is 3,200, and converting to inches obviously is in there. And then divided by 2, I get 153,600 inch-pounds. Plugging that in, that's my M value, sigma is MC over I. And I could have used the section modulus from the last time, but I chose to use, I could have just done M over S. This is sigma is equal to that number there, c, the distance from the neutral axis to the outermost fiber, that's c, okay? And then I is BH cubed over 12, base is 7.5. H is 11.5 over 12, you get 929.1 inch-pounds. I'm sorry, PSI. And you could have easily just used that formula, calculated that value, plugged it into that. So there's a few ways to skin this cat. That's where we're getting at, okay? Next question. Same beam, assuming that due to construction error, and we know that never happens, right? The beam of the previous two examples was placed incorrectly in the field and the small dimension was up vertically. That's a big problem, right? Because basically you're reducing the moment of inertia of that section, and moment of inertia speaks directly to a beam stiffness and how much it doesn't deflect. For the same span, length, and loading, so 16 feet apart, 400 pounds per square foot per foot, calculate the new maximum bending stress. So the bending stress of the last problem we calculated to be 929 psi, right? So here, if just, and all this is going to do is the moment of inertia calculation stays the same, but now the base is the long dimension and the height's the short one. If you just swap that out, remember, I is now larger, is now smaller. If I is smaller, stress is going to be higher, inversely proportional. This is smaller, that gets bigger. This is bigger, that gets smaller. I plug in that new higher I, now my stress shoots up to 1,424 pounds, PSI. That's 65% higher than the previous example, just by putting the beam the wrong way. Same beam, same loading, not follow instructions, makes the problem, makes the issue 65% worse. Like I said, details matter. Okay, let's go change course. No more of that wood beam. Let's use a W beam. W 30 by 99 hot rolled structural steel wide flange shape. And when you have this designation, the 30 is the approximate height of the beam, and you'll see that this one's going to be 29.7, and the 99 is approximate weight per feet, right? 99 pounds per foot, right? It's used as a simply supported beam on a span of 32 feet apart. The beam supports a superimposed UDL, 4,000 pounds per foot. In addition to its own weight, calculate the maximum bending stress. So 4,000 pounds per foot and the weight. So let's just combine the UDL. Instead of just being 4,000 pounds, let's put the weight in there as well. So it's 4,000 pounds plus the 99 pounds per foot. The total UDL is 4,099 pounds per foot. So we can look at the appendix in the back. Appendix A for the beam, this W by 99, page 486. Sometimes you gotta know how to hunt these out. Okay, and I can show you the best I can. Here's Appendix A for a member, W30 by 99. That's the beam there. You can get the cross-sectional area, the depth, which is that D, 29.7, which you spoke of earlier. Here we want the moment of inertia, 3,990 inches to the fourth. You can also get the section modulus, which has the C dimension built into it. So you can use that, or you can use that and everything else you have, okay? This question's asking for the bending stress, sigma equals MC over I. I'm choosing to do it with C and I. So C would be the 29.7 divided by 2. That's how I get that number there, right? Or the depth divided by 2. And I is going to be off the chart, which is 3,990 inches to the fourth. This is a UDL, same exact problem. If we go to page 503, that's in Appendix H. Okay, this is still case 1. And the max moment, instead of doing a long drawn out shear moment sketch, max moment is WL squared over 8. That's what I have here. So I can simply calculate that maximum bending moment, 524,672 foot-pounds. Plug that in and get my bending stress value, 23,000 and change PSI. Okay? Pretty straightforward. Last one Example 4.5, page 307. This is a pipe, right? Standard pipe. Having a nominal diameter of 127 millimeters is used as a simple beam to span a length of 7 meters. So 7 meters across. The pipe supports a concentrated load at the midpoint of 6 kilonewtons, right? Calculate the maximum bending stress due to the weight of the pipe alone and then the concentrated load alone, right? So this is going to have a pretty good weight. This weight is going to make this thing sag a little bit. So we want to know what the stress is just because of the weight of it. And then we want to know the stress of it just because of the concentrated load. So this, the dimensions of the pipe and some information can be found in Appendix B, page 489. Okay, here's a table. Selected pipes, dimensions and properties, right? Here is nominal diameter 127. You can get the OD, the ID, all that. And in this question, we're going to know, because we want to know the weight of the pipe. It doesn't have weight, but it has mass. And you guys should know from elementary physics that weight is a vector and mass is a scalar, right? And weight is equal to mass times gravity. We'll get to that in a second. So I'm going to take that. I'm going to take the section modulus. But with everything here, I can easily calculate I or C. But I'm going to grab the section modulus this time. You can do it either way. Okay, 127 millimeter pipe, 30.9 kilograms per meter. That's a scalar, right? We got to convert that to a vector quantity, right? And then the section modulus, what we just said, 115, 10 to the third millimeters to cubed. So here, better to use S instead of I over C because the X section is unknown. Actually, the X section isn't unknown. We can look at it in the table and figure out what the cross section is and do it that way too. Let's take that mass value, convert it to a force, which is a weight. Mass times gravity, 30.9 kilograms per meter, times 9.81 meters per second squared. That's gravity, right? The acceleration due to gravity. Physics 101 should have taught you that. We get a weight of 303.1 newtons per meter. So this pipe weighs 303 newtons every meter it is long, okay? So let's just, part A is, what's the stress in the, bending stress in the pipe just for the weight of the pipe? This weight is obviously UDL going across, 303.1 newtons per meter over 7 meters. Just like the last example, that distributed load, Appendix H, page 503, the maximum moment is WL squared over 8. Easy to calculate, 1,856 newton meters. Plugging that in, M divided by S, which is the S we grabbed from the chart. Easy, 16.14 MPa, metric unit of stress, megapascals, right? Newton per millimeter squared, right? Part B is, what's the stress due to the concentrated load? Concentrated load alone is simply the 6 kilonewtons in the middle. Same thing. This is now Appendix H, but it's no longer case 1. It's no longer this case. It's now case 5, where the simple beam concentrated load at the center, we see M max is PL over 4, where P is the load, L is the length, and you divide by 4. So these tables, Appendix H is pretty handy in doing these problems. You don't have to do a full-blown shear moment diagram, right? So M max 10.5 kilonewtons per meter. The section modulus is the same. You do that, you get 91.3 MPa. So if you put them combined, which is really a real-world problem, the stress due to the weight alone of the pipe, 16.14 MPa. Due to the concentrated load you're trying to hang on it or put on it, 91.4. If you add those together, roughly you get, what is that? 101, 107, 108 MPa combined. So that would be the weight, that the question doesn't ask that, but the combined stress due to the weight and the concentrated load about 107 MPa. Okay, that's everything we're going to do in class. You can see these questions are very straightforward. They're all based on the fact that you know how to use the tables, how to calculate shear moment diagrams. But once you have all that, that's the hard part. Calculating the actual bending stress is a very simple and straightforward process. Okay?